video as well. So without further ado,
Okay.
Danny, as engineer in charge, take it away.
Okay, guys. Good morning, Durham and Stockholm. Good morning.
Good morning. Hello.
Very good.
I will need some kind of feedback. Okay. That's all I'm asking. Okay, guys. So I hope you all read this document. It's on Sakai, and my intention here was to show you how the analysis and the testing is done in industry. So this document is pretty much goes over all of the steps that we do whenever we need to validate or to analyze some kind of structure for flutter. And so we won't get into Hamilton's principle here.
Oh, good.
So we will do
Or turbo machinery.
what?
Or turbo machinery.
Or turbo machinery. Yeah, this is
No, it's not yet.
yeah. So these are all standard commercial tools, and the way that I see it, I will go over this document, and then if you have any questions, you are welcome to ask. Will this work for you?
Yeah, works pretty fine.
And you? Okay.
We have a nodding of heads.
Okay. Okay, guys. So we'll start. So first of all, this is our structure. This is a thin plate shaped like a delta wing, made of aluminum, and there is no particular reason for me to choose this, except that I found this in our warehouse. So this is the reason for this structure, and no other one. Okay, so the first thing that we need to do is do our model analysis. And this is done in order to obtain these shape functions that we refer to as Xi. Okay, so Xi functions, and also we need the natural frequencies, and other stuff like generalized mass matrix. And that's it. From these two, you can get your K matrix, the generalized stiffness matrix. And this is done in commercial finite element code. In industry, every elastic analysis is based on model parameters. We are not putting inside the actual physical model. We are using the resultant model, which means that I need to provide to my Aeroelastic software only these parameters, and that's it. The software doesn't care the material, the boundary conditions. Everything is already here. Okay. So because we have a simple structure which is a thin plate, the very simple way to represent it is with plate elements. You can see it here. Okay, I will not go inside of there. So after we done the analysis, we have this results, which first bending is around 4 Hertz. First torsion is around 16 Hertz, and there are a bunch of other modes which are we are less concerned about them, but they are there. Okay. So other stuff that we need to see is the associated mode shapes. So this is first bending, first torsion, and more complicated bending and torsion stuff. Yes.
In industry, would you use a simplified model like this, or would you use the whole big model?
This is a whole wing model.
So you would just use a simplified plate in industry, or would
Well,
you use a more complex?
Well, the modeling, the structural modeling is very connected to the actual structure. This structure is thin plate, so it's very logical to represent it with plate elements. But if you have something more complicated, then by all means you can go with solid elements, whatever works for you. Okay. So for this particular case, this is very logical. We don't need to search for something else. This is very simple to represent it with plate elements. Okay. Okay. So now we've established our model, our structural model. The other part of elastic analysis is the aerodynamic model. Aerodynamic model is the one that will generate us the non-steady aerodynamic loads. Okay, so all that you need to do in commercial code is just to say where your plate elements are. So this is our aerodynamic model, and just crafted our model with aero boxes, and each box will generate us the unsteady lift and moment. With it's more generalized. It will actually generate us 6 degrees of freedom for 3 forces and three moments, but some of them might be 0 because they aren't really in, for example, in plane motion for aerodynamics. Okay, like I written in the document, one of the most important things to verify is the transition between the aerodynamic and the structural model. This is super important. Ask me how I know.
How do you know?
With hundreds of analysis and a lot of mistakes. Yeah, it's the only way to learn. So you see in yes. Sorry.
How it is done in software? Have you applied possible on both sides?
No, in software, the way it's done, it's you say what's your lifting surface is. This is your lifting surface, and then you just say, okay, I'm flying at Mach this and that, and that's it. And you leave it to the software to generate the actual forces. Okay, very simple. but no, this software is called Zero. It's commercial software. It's like state of the art in the industry. In the industry, you have 2 standards. You have Nastran. They have a portion of elastic analysis, and you have Zero. These are 2 software that will do your very good linear elastic analysis. Okay. In my opinion, because I'm familiar with Zero, it's more advanced. Okay.
Use an Everest equation or some different kind of equation?
Sorry?
Does it use Everest equation or some different kind of equation?
Okay, the model is based on doublet lattice.
It's based on linear potential flow theory, which will be covered in chapter 4, so you'll hear about later in the course. But you're basically solving the convective wave equation subject to certain boundary conditions. And so in the aerodynamic code, you specify motion in one of these structural modes, and the aerodynamic code will find the pressure on the wing due to that mode. Since we use a linear model, that means we can superimpose. So we do that for each of the structural modes of interest and add those all up together, and that gives you the total pressure on this wing. And from the total pressure, you can find the internalized force, if you remember what the internalized force is. And what the code really outputs is internalized force. And they do it for simple harmonic motion in time, which, if you do not know it already, will be sufficient to do the flutter analysis.
Okay. So that's a little validation step. We should plot our structural modes in aerodynamic grid, just to see that there are not any issues in there. So we have our three modes. This is the first torsion, and this one is second bending. Okay. So now that we are done with all the preliminaries, we can run the flutter analysis. And the output of flutter analysis is this graph. It's called the VG-plot. VG-plot is a really standard way to represent our flutter results. So basically, the upper portion of this plot is our structural modes, which vary with airspeed. Airspeed is on the axis.
Frequency of the structural mode.
Sorry, yes, the frequency, of course.
Yes.
Okay, and the lower portion is our total damping, and yes, whenever the damping is negative, we are very happy, and once the damping becomes positive, it means that we are going to flutter. This is our solution for flutter, the transition. Okay, up till now, we have covered the entire analysis. Questions?
Question,
What is going to flutter? Yes, but if you remember last lecture, you don't have the luxury of fluttering part of the structure. Everything will flutter. Okay, you can't live with this. Okay, if one mode becomes unstable, the whole structure is unstable. Okay.
The other thing to point out is that the structural modes are the modes that exist when the velocity of the flow is zero. Okay, because when the velocity of flow is zero, you have certain natural frequencies of the structural mode, and the damping is zero in all those modes unless you've assumed some amount of damping in your structural model. But once the airflow exists and you change the velocity, then you have aeroelastic modes which have aeroelastic eigenvalues as both the frequency and the damping. And each aeroelastic mode is no longer a pure structural mode. It's a linear combination of the structural modes. And since also you don't know ahead of time which particular structural modes will combine in a certain way to produce flutter, you need to include enough to make sure you haven't left something out. There's always the possibility you have left something out, and there are famous examples in the history of aeroelasticity when people left something out and then when they test the wind tunnel model, it fluttered, much to their unpleasant surprise. Yes.
So you're able just to see which is the dominant mode, but you don't know which other modes are contributing for that.
Oh no, you can. If I go to say the flutter point, the flutter condition, that's a certain velocity. It's by definition zero damping, and it has a certain frequency. Then I can go back and look at the eigenvectors of my math model. The eigenvector will tell me how much of the first structure mode I have, how much of the second, how much of the third. And by the way, they're phase shifts, so these are all complex numbers in general. So in general, there's both a real and imaginary part of the math model, which corresponds to in phase and out of phase of the modes. So you can find the actual shape at which, in fact, did you do that? I don't know if you have you could from the math model you could predict a video showing the shape of the ring.
Are you able to do something like that through experimental results?
You will. I hope so.
We hope so.
We hope so that you will see the actual flutter on
So
surface.
you're putting like string gauges in different directions.
Well, you see it by eye.
We will talk about this in a minute in the instrumentation phase.
Okay.
Okay. Questions in Durham?
Yeah, I have one question. When you did the structural analysis in ANSYS, did you consider the pressure forces acting on the wing, which is causing the softening of the wing and hence the frequency is decreasing?
No, the answer is no. Actually, when you do in ANSYS or in any software for the matter of fact model analysis, it automatically assumes that the right hand of your equation is zero. So no matter what you add as your load, it will not consider it. For the other part of this question, if you look at this graph, these are my results of the model analysis. These are the frequencies at zero velocity. But once you proceed, you will have your softening, stiffening as a function of velocity. You see here, this mode, for example, it becomes softer once we increase the velocity. Okay, but really you need the set of your basic modes and eigen frequencies.
Danny, you might want to indicate which of those frequencies corresponds to this
Yeah.
order form. I don't remember which one.
So in the PDF file you see it better, but this branch corresponds to the torsion, to this mode. This is the torsion mode, and this one becomes kind of stable. This is the bending.
Yeah.
Okay.
So it isn't necessarily the lowest mode.
Yeah. It's the second.
But again, that's a flutter condition. It's really a linear combination, and I think in this particular case, it's going to be first bending and first torsion. Both
Yeah.
are significant.
Yes.
The other modes are less so.
Yes.
Oh.
Okay. Question?
Okay, thank you.
Okay, so we go to the last part of this this document. We're talking about instrumentation of this wing. So my aim in this test for you to see this part. So what I want us to see is the two modes, two separate modes, which will combine to one flutter mode. If you remember from this document, the solution is flutter at around 12 hertz. So 12 hertz is very nice because you can see it in your eye, with your eye. Okay, everything is below 20, 25. You can actually see. So this is a good experiment. Yeah. For example, in not very recent case I had back home, we had the flutter at 150. You see nothing. You need to rely on your instrumentation. That's it. Okay, so for the purpose of seeing each mode separately, I did instrument this wing, and I hope it will work as it should. So we have two bridges here. This one is the bending bridge. It's located at the highest bending strain location.
How do we know that?
Well, if you bend this plate, you will have some kind of hot spots. Okay, and the location of this one, this is our torsion bridge. This is more tricky. Can you see why is it located there? This was a question. What? Yes, this one is really easy to see. This one, the bending, but the torsion is kind of more subtle. If you look at the torsion mode,
Put that up a little further.
yeah, this is our torsion mode, and you see here is the nodal torsion line. So this is the line that the wing will twist around. So what I did, I put gauges in these locations, just to see. In this mode we have no bending, and we wanted to sense, to measure only the torsion motion. So around the nodal line, it should be the better location for this mode.
So here's a case that's not flutter, of course, but here's a case where you think that the eigenvector of your structural mode analysis, and from that you can find the shape in that mode in which the plate is vibrating. And if you show back that figure again, it's hard to see in this picture, but here's a color code, and you see there's a larger deflection here, and then it goes with a minus sign, and then it goes essentially to 0, and then it's plus, indicating there's been a change in sign because it's twisting. The torsion is positive in one side of the plate, the deflection is positive one side of the plate and negative in the other, and it goes to a 0 point. And in fact, it's a two-dimensional object, so it has a whole line of zeros about which the torsion is taking place. So you get a lot of information out of this, yes.
regarding the instrumentation, how likely is that you reuse that wing after putting the strain gauges in there? Is it going to change whenever you try to take them out?
That's a good question.
Again, you're asking if by
You can
putting.
reuse them experiment because you have them already stuck there and probably it's
Okay.
going to change some.
If you want to use the wing in another experiment, you are welcome to do so. But if you want to detach the strain gauges and use them on separate different extraction, no.
You could use.
Yeah. But of course, this model, if we don't break it,
Yes.
It-
Assuming we don't break
it will stay here, and you are welcome to use it afterwards.
Yeah, as long as you stay within, below the yield stress of the material in the
Yeah.
oscillations, you can, because it's still in the elastic range. But sometimes if you, well, you'll see in the test, I don't think we're gonna go that far, but if you ran the airspeed high enough, the oscillations get large enough, that some portion of the wing would have a stress level exceeding the yield stress of the material, and you would plastically deform it. And once you plastically deform it, it's not usable again.
Yeah.
Right.
Strain gauges will continue working up until like 2% of plastic strain. 2% it's enormous strain. It's plasticity. But afterwards, you can't really rely on the readings.
What are the directions?
The what? Directions?
Yeah.
Okay. Yeah. So I'm using actually 4 every time. These are 2, and we have the complementing couple on the other side. So okay, so it has to do with the Wheatstone bridge. Okay, because in every instrument that reads strain gauges, it implements Wheatstone bridge in this way or another. If you are taking, for example, if you're buying load cell that's strain gauge based, inside you have your Wheatstone bridge. Okay, Wheatstone bridge, you have 4 wires. 2 wires is V in, you feed the circuit, and the additional 2 wires is V out. Okay, but this principle, it's very useful for us to do a custom load cell. This is custom load cell. Okay, I'm just using this principle to instrument what I want.
Basically, this is full bridge model.
Full bridge.
You could have gone for half bridge also.
So what?
You could have gone for half bridge model also, where you will be using only one strain gauge.
Yes. Yes. The reason for it.
Is it related to redundancy also?
Is it what?
Related to redundancy also?
No, it's not redundancy. I wanted to amplify the signal. With full bridge, you can this bridge is amplified actually by 4. You need this because the readings of the bridge is in millivolts, and you need to accommodate all of your hardware capabilities. Okay, so you want to have to apply the signal. Okay. Yeah. Sorry? Okay. This one you understand, right? If you bend it, let's do it like here. This is our wing. So here we have, this is longitudinal direction and this is transverse. Okay. Once you bend it, this will have some kind of strain, and this will have minus ni epsilon. Okay. So on the other side couple will have minus epsilon and plus ni epsilon, right? From the other side. Okay. So you can wire your gauge. Let's call this 1, 2, 3, and 4. Okay. This is standard wiring for bending bridge. The advantages of full bridge is, for example, the temperature effect cancellation. I'm not considered with any drifting in this particular case. And also, I can wire this like this. I can wire this as epsilon 1 minus epsilon 2, epsilon 4, sorry, plus epsilon 3 and minus epsilon 2. Okay, so here I have an amplification 2.6 because Ni is typically 0.3. So I really like this. Okay, I want to be able to use this amplification without paying for it. Okay. So and the other bridge is pretty much 45 degrees around the nodal line, because if you twist the cylinder, the twisting stresses will go on the 45 degrees. Okay, so this is a standard. Actually, if in this way you do, if you want to instrument your aircraft for flight test, this is the way you do it. Okay, if you want to measure the loads on the wings, on the structure, or in any place on your aircraft, this is the way you do it.
In a flight test, how many strain gauges would you typically have?
In a flight test, you're usually limited by the instrument that you have on board.
Yeah.
So typically, if you have 50 channels, you will use all of them. Yeah. So this is in.
Okay. And if I didn't want to use strain gauges, I have an aversion to strain gauges.
Okay.
What other instrumentation might I use?
Okay. So the other stuff that you can use, pretty basic, is accelerometer. But accelerometer is it has a volume. So you, for example, you can put one here, but your flow will not be the same. It's a brick. So for that purpose, strain gauges are the most concealed instrumentation that you can use. In addition, you can use non-contact displacement meter with laser beam. So this, but you have to have it in order to use it.
Yeah, but now that would be used in a wind tunnel test. Would you ever use something like that in a flight test?
No, in flight test, the way that displacement meter works, you should mount it somewhere, and then it measures displacement related to this mount. In flight test, you cannot use it. So in flight test, it's usually only accelerometers and strain gauges.
Yeah, frequency is quite low. We can also go for high-speed cameras.
Sorry? Yeah.
Frequency is low, we can go for high-speed cameras.
You're right.
Yeah.
Yeah. We have high-speed cameras.
There are high-speed cameras.
Okay.
Yeah.
If you can get one, we can use it in the test. Yeah.
And how are we able to distinguish between which modes are vibrating with the accelerometer?
Okay, so in the way that I set it up in the test, you have two readings from each of the bridges. One reading is your typical called millivolt per volt. This is your reading of this bridge. Okay, the amplitude, and also we have it on the frequency scale. We do a quick FFT of these two signals.
So the accelerometer is giving you signals?
No, not kilometer.
So that's what I want to know. The accelerometer, how are you able to simulate the same thing, same kind of experiment that you're doing now with the strain gauge? How are you able to get those modes? Okay, accelerometer, you would have we have to have a little more work, because accelerometer measures only linear motion. You cannot distinguish them, but potentially you can put one here and one here, and once you sum them, once you differentiate them, maybe in this way.
But note that Danny used some foreknowledge based on the analysis as to where to put his gauges.
So you can do the same thing for the accelerometers.
You could, in principle, yeah.
Yeah.
No. One thing you haven't talked about is, have you measured the natural modes on this plate as yet?
No, not yet.
Do you plan to do that before you do the flutter test?
Yes.
Are you going to do that on Thursday?
I hope so.
Okay,
I hope to do it tomorrow.
Okay.
But I will continue on my talk. We will have our frequency reading of these two bridges. So potentially the ideal thing that you will have the bending reading around 4 Hertz, and the torsion reading you will have around 15, and you will have them shifted.
If we will be measuring 1 and 2 separately, then we can say if it is going to pure bending, some value of epsilon we are getting from those two, we can say that it is going to on bending mode or something like that.
You are talking about accelerometers?
No, if we are measuring like 1 and 2, those are 90-degree apart.
Okay.
Yeah. So if we are measuring it separately, so from the values we can say that it is likely to be going pure bending, or it is going to torsion or something like that.
For 1 and 2, or only here?
Yeah, 1 and 2. Because one is epsilon and other is
no, because you wherever you instrument something, that your goal is to go beyond the noise level. So let's see, for example, here this is the torsion mode, okay? And here there are no actual readings. Okay, you don't want to put your instrument there to measure this mode.
Now, if we are getting torsion mode and we have to put our instrumentation on the corner right there.
Okay.
And if we are not getting any good input from there, we can say that it is not going for bending. It may be a torsion. And when we are going for bending mode, we will see the readings there. Okay, prominent reading there.
Well,
so we can say that it is likely to go into for bending mode.
Well, if you don't know what your instrument is supposed to give you, this is all a guess game. Okay, so yeah.
Yeah, you certainly want to do the analysis first, because that gives you some guidance when you start making the measurements. Also, each of these instrumentation arrangements, they're designed to emphasize one mode or another, but each of those strain gauges will presumably give you a response at every resonant frequency. Okay, it's just that he's cleverly chosen the location for the bending mode to give you mostly bending, and probably primarily first bending, and then he's chosen a clever location for the torsion mode to primarily emphasize first torsion. But you'll see other responses. If you look very closely, you don't have too much noise in the system, you'll see little peaks at various frequencies correspond to all of those resonant frequencies that you calculated. And of course, if your calculation is fairly accurate, then you can identify which mode you're at by saying, oh, I calculated it's going to be a 4.6. I measured mode at 4.5. That's probably that mode, right? Yeah. Now, if it turns out your calculated frequencies are way off from your measured frequency, then clearly there's an issue.
We hope not to get that. One other thing about the modes, it's the way that we name them. So let's say we are talking about not a simple plate, but an aircraft. In aircraft, you also have the first bending mode. But the thing that you need to remember always, that in first bending mode, wing bending mode, all of the aircraft responds. It's mostly bending mode, but all of the aircraft is in motion. This is very important. This is very important for when you do your test and some manager comes and asks for it. So it's very good answer. Okay, so the naming is arbitrarily. Okay, so we choose them, but according to the most motion at this mode. Okay. No, this is the name. So we like first bending of our wing. Okay, but the fuselage will respond. Yeah.
We have another question.
Yeah, you mentioned the differences in testing between, or alluded to the differences in testing between in wind tunnel and in flight.
Yeah.
I'm just kind of curious about how you would test a flat plate in flight, because I can't think of any aircraft that.
No, it's.
Yeah.
You could. I mean, I can take an airplane and I can take that flat plate and mount it on the airplane and do a flight test. I'm not sure why I want to do that, but you could.
Well, it just got me thinking about if you were testing in flight, you probably would be able to fit accelerometers within the wing that wouldn't disrupt the flow.
That's
So
right.
what's the sensor of choice for in-flight testing? What's most accurate?
It's not a matter of accurate. This is actually it goes by departments. The environmental guys that usually measure vibrations and stuff, they like accelerometers.
Yeah.
The structural guys, they like very much strain gauges.
Okay.
This is very separated because if you want to validate your, for example, your loads model, there's little to know from accelerometer. You can, but why would you if you can measure it directly?
Yeah.
It's also a matter of robustness. The things that are survivable in wind tunnel may not be survivable in flight,
Yeah.
right? And even in the wind tunnel, it depends on whether you're doing a low speed test, as we're going to be doing, or whether you're in a transonic or a supersonic tunnel, where the flow environment is harsher. And so instrumentation that you might use in a low speed test might not be suitable. Also, in transonic flow, to be much more concerned about any instrumentation disturbing the flow. In the low speed case, you disturb the flow a little bit, probably doesn't matter all that much. But if you're in transonic conditions, you disturb the flow, you might create a shock, you might move the shock from where it was without the instrumentation to some other place, and that could be an issue. All kinds of difficulties. So it's robustness, and on the one hand, ruggedness, survivability, and on the other hand, you don't want to disturb the flow, particularly in higher speed flows, which are more sensitive.
Yeah. So in this case, the shielding will be much better in transonic flow or supersonic flow.
We should give our friends in Stockholm a chance to ask questions.
Yeah.
We've been having a lot of questions here in Durham. Well, I'm sure there's some penetrating, difficult questions that you would like to ask Danny.
Hey guys,
Are they still there?
are you there, Stockholm? Stockholm?
No questions here. We are right. Nice. Thank you.
Sampling rate? Well, I'm just discovering the instrument that they have downstairs. We'll have enough sampling rate for.
But normally, which one would you use relative to the?
Well, usually you want to sample it at least twice the dominant frequency. This is the Nyquist ratio. But if you just sample it like 20 times more, something like this. Because what Nyquist doesn't tell you, twice the frequency, you won't get the actual amplitudes. You will get the frequency, but the amplitudes will be clipped. So if you can, just sample like 20, 30 times more. But you might run into some instrument limitation. Okay, it's not in our case, but potentially you can. Okay. Okay, guys. Thank you.
Okay.
See you on Thursday.
All right. Thank you very much, Danny. This is a special treat for me, and I think, although you don't have the experience of having the course out there. So take my word for it. This is a special treat. And thank you, Danny, for preparing that for us. Let's see. Homework is due today, right? Oh, I'm so excited to get that and have the opportunity. See, today is the, don't tell me, it's the 7th, is that right? Very good. So it's the 7th of February in 2017. Several of you, perhaps motivated by the homework, that's one reason we offer homework, to motivate you, right? It should be, in principle, sufficient that you are just seekers after knowledge and thirsty for new capability. But sometimes if you assign homework, it does focus the mind. So several of you have come by and asked about Hamilton's principle and some of the more subtle aspects and how is it mathematically made more rigorous. And I wanted to mention one book in that regard. Let's see, I'll put it up here. There it is. This is one of my favorite books because I use it just a few years ago when I was a graduate student. And I actually took the course from Professor Hildebrand, who gave a fantastic course. There's a chapter in here on the calculus of variations, which is the mathematical underpinning of Hamilton's principles and some other things as well. So let me point out to you that in chapter 2, there it is, calculus of variations and applications. And you'll see he talks about a lot of things. He talks about Sturm-Liouville problems. He talks about Hamilton's principle, Lagrange's equations, and so forth and so on. So this is probably, if you want to know a little more, one of the better resources. Now, you cannot all borrow this book at once. On the other hand, let's see. Yeah, this is available in a Dover edition. I forgot what it costs, but not very much, right? So if you want it for your very own. And he also covers some other things that might be of interest to you. He covers matrices and linear algebra. That's chapter 1. And then the calculus of variations and applications have chapter 2. And then integral equations, which we're going to study in this course as well, is chapter 3. And that's it. Only 3 chapters, but each of them is moderately long. But the whole book is about 300 pages. And so highly recommended to you. You may peruse it briefly if you want to look at it to make sure you want to actually purchase it. You're welcome to do that. In fact, why not pass it around? So, I'm sorry, Stockholm, I can't pass it around in Stockholm, but I'm sure it's available to you over Amazon or some other reliable source. Now, with that said, we're now prepared to do the dynamics of linear systems. And you might ask, why in the world are we doing that? Well, if you understand the dynamics of linear systems, you'll be ready to do a flutter analysis and also some other things as well. So we're going to go through this moderately quickly, but you are free to slow me down at any point because people do offer courses for an entire semester on the dynamics of linear systems, and I plan to cover it in 2 or 3 lectures. So no, I'm not going to say everything there is to be said. I'm just going to say everything that's important to be said. Well, that's a little joke there. Okay. Now, in the book, I consider an example. I'm going to take an example because I think we take a concrete example of a certain dynamical system, it'll be a little more meaningful to you. So I'm not going to use the one in the book, though, right? I'll use one that was studied in your first homework. The mathematics is exactly the same. The ideas are exactly the same. Everything's exactly the same, except I'm taking a different system with a different equation of motion. So I'm going to take the one that you remember from your first homework, which is something like this. Alpha dot dot. Yeah. Okay. Oops. Yeah, I guess I can see that. And this is written in non-dimensional form. Plus omega alpha squared. Remember, omega alpha is the natural frequency and torsion of my system. 1 minus Q, the dynamic pressure over the divergence dynamic pressure, times alpha equals, again, Q infinity over Q divergence, omega alpha squared, omega alpha naught. Remember, alpha naught is the angle. Thank you. Is the angle at which the airfoil is placed before the torsional spring twists, right? And just to make life a little more interesting, I'll also put in a damping term, structural damping term. Okay. So you can put a structural damping term in there if you want. But now, at some expense, I'm going to think of having built a wind tunnel model, or it's just a math model if you prefer,
where I can let alpha naught be a function of time. So I can, right, change this function of time. I can change the direction of the flow, or I can orient the aircraft so that it's at a different alpha naught, even though there's yet no twisting of my wing. So now alpha naught is a function of time. Because if it isn't, I don't have any dynamics, right? So that's why I want it's a function of time. Now, I'm going to let alpha naught as a function of time be alpha naught bar cosine omega t. And then I'm going to let alpha be alpha bar c cosine omega t plus alpha bar s, sine omega t. Because it's a linear system, I know that the frequency of the input is the same as the frequency of the output. Can't happen, nothing else can happen. But I do need to allow for the fact that there's a phase shift, right, between the input and the output. And in fact, I can continue to use this notation, but no one does. Instead, what we do is we say the following. We say alpha naught is alpha naught bar e to the I omega t. And then by convention, we say, well, what I really mean is really mean the real part of this complex number, which is exactly that. Okay? And alpha is alpha bar e to the I omega t. Now, alpha naught is a real number, right? But now alpha bar is a complex number with both a real and imaginary part. So I'm going to write this as alpha bar real cosine omega t minus alpha bar imaginary sine omega t plus I times what? Alpha bar real sine omega t. What else? Alpha bar imaginary cosine omega t, right? I can do that, all right? But if the convention is I take the real part of this, so it's just alpha bar naught cosine omega t, then I got to take the real part of this too, and I do the calculation using complex numbers, but at the end of the day, if I really want to know what alpha is, I take the real part of this complex number, right? Which allows for the phase shift. But using the complex notation is a much more compact and efficient way to do the algebra. That's why people do it. And it's okay. But if you've not done this before, you may want to think about it. By the way, I could have done the other thing. I could have, by convention, taken the imaginary part of this as the physical part, but then I would have to take the imaginary part of this. I would get the same answer. Okay, as it turns out. So, yes.
So alpha naught, which is the angle of zero twist, is changing with time.
Alpha naught is changing with time, yes. And I'm assuming now that it's changing with time in a very special way. It's a sinusoidal motion at one frequency, or a harmonic motion at one frequency, namely omega. Yes.
But alpha naught is the angle where there's no torque.
No twist.
No twist. Yeah.
Yeah.
So
you're going to press me on the physical plausibility of this?
Yeah.
Forget about it. This is an exercise. But I tried to rationalize it a moment ago, but I don't want to overstate it. If I have an airplane, I have a wing, right? I could think of orienting the airplane, right? And the twisting always takes place relative to the fuselage. So I'm changing the fuselage angle relative to the flow. That's alpha naught. And then alpha itself is the twisting of the wing relative to the fuselage. Does that make you a little happier?
Yeah.
Okay. Gee, you people are tough. Okay. All right. So I'm going to call this equation 1, right? And this will be 2. and this will be 3. And of course, I'm going to put 2 and 3 in 1 and see what I have. Since it's a linear system, everything's going to have an EI omega t, which will cancel out. And so I'm left with the following. I have minus omega squared, minus omega squared because it's alpha double dot, right? Each derivative of certain time generates an I omega, and it's I omega squared, which is, I'll have plus my omega alpha squared times 1 minus q infinity over qd all of that by alpha bar, because there will be an alpha bar in each of those, equals q infinity over qd omega alpha squared omega naught bar, right? Alpha naught bar. And just to remind you, if I want to put in structural damping, that's this term, right? Then that will add 2 zeta alpha omega alpha times I omega, right? Because an alpha dot generates an I omega. So it's a complex number on the left-hand side, definitely a complex number. And alpha bar in general is a complex number. And alpha bar naught is by definition not a complex number because I don't need it, right? I mean, I can specify a certain oscillation. Okay, now it's a linear system. Therefore, I can calculate alpha bar over alpha bar naught. And it turns out to be q infinity over q divergence omega alpha squared, that's the coefficient of this, divided by all this other stuff, minus omega squared plus omega alpha squared, 1 minus q over q divergence. And then I'm going to add in the damping term too, plus 2 zeta alpha omega alpha I omega. Okay? So 2 plus 3 in 1 produces 4, and rearranging 4 produces 5. Okay? Now, I'm going to define this ratio and all this stuff as a quantity, which was usually known as the transfer function. It transfers alpha naught into alpha. Okay? So this is the transfer function. So I'm going to define this as h alpha alpha naught because it tells it's some function h, but it's related to alpha naught and alpha. And it depends on lots of things, but most importantly, it depends on omega. So that's the dependence that we really want to think about. But it also obviously depends on omega alpha, right? It depends on zeta alpha. It depends on q infinity over q divergence. And I guess that's it, right? So this simplistic model, it is simple, shows a couple of things. It shows that the transfer function depends on frequency, but it also has some parameter dependence. It depends on the structural character, it depends on the resonant frequency of the structure, it depends on the amount of damping in the structure, and it depends on the flow. Now, this is a particularly simple dependence on flow. As we'll see later on, this I will call a structural transfer function because it's a structural equation of motion, right? But there will be an aerodynamic transfer function. The aerodynamic transfer function will be the pressure or the aerodynamic forces on the wing due to a prescribed motion. And then there will be an aeroelastic transfer function, which is a certain combination of the aerodynamic plus structural transfer function. But since it's all going to be linear analysis, linear dynamic analysis, the concept of the transfer function is key to both the structural modeling and the aerodynamic modeling. Okay? So far, so good? I see lots of nodding of heads in Durham. How about in Stockholm? Are you still with me?
Yes, we are perfect. Thank you.
All right, fine. Now you have gotten onto the slippery slope. Once you accept this, it's all downhill from this point on, right? Okay. So let me rewrite that. All we need to know is that there's a transfer function. Okay. Using higher mathematics, alpha bar is alpha bar naught times the transfer function. I won't always write all the things that the transfer function depends on, right? Although maybe in this case I should at least let you know it still depends on omega. But now let's say alpha naught is a little more complicated. I now want to look at periodic motion, which is a result of periodic inputs and periodic outputs. So I'm going to let alpha naught be a little more elaborate. I'm going to let it be a summation over n of alpha naught super n e to the I in omega naught t. Omega naught is still the frequency, okay, of the input. And if I only have one term in this series, i.e. n equals 1, it all goes back to what I had before. But now I wanted to have lots of terms. Why? Because any periodic motion can be represented, any periodic function of time, including a periodic motion, can be represented in this way. But because it's a linear system, once I know that alpha naught is represented in this way, I can immediately write down alpha itself in this way, right? How can I do that? I'm glad you asked me. Yes, right.
The n in alpha naught is up to the power or just an n?
You're talking about n?
Yeah.
I'll tell you. N goes from minus infinity to plus infinity.
No, but I mean, in the alpha naught, so it says alpha naught and to the power of n, or it's just an index?
Oh, this one?
Yes.
Oh, this one it doesn't depend on time. It's a coefficient.
So it's just okay.
Yeah, I'm going to show you how to find it in a moment. But you're one step ahead of me. I'm going to show you something else. First of all, I'll show you why it's useful. Then I'll show you how to compute that coefficient. Okay. Okay. The reason it's useful is if I want alpha now, alpha is just the transfer function. Well, let's see. Yeah. Using 6 and 7 is just right the other way. It's clearer. It's just this. It's a summation over n of alpha naught n h of alpha naught, where omega is now set equal to each of these frequencies, right? So I can put an n on that. That's what the n means. It means each term omega is replaced by n omega naught. And then, of course, it's E, I, N, N, omega naught T. Right? You agree? Okay. So now I'm ready to answer the question, what's that? Right? So the idea is, you tell me, it's got to be, this function can be anything, but it's got to be periodic in time. That is, it has to repeat every so often. And if omega naught is the, if you will, the fundamental frequency, or the first harmonic, fundamental frequency, then T naught equal to 2 pi over omega naught is the fundamental period. That is, this is how long I have to wait before before alpha naught repeats itself, and also how long I have to wait before the motion repeats itself, because alpha and alpha naught both have the same fundamental frequency and the same fundamental period. Okay. All right. So now I'm going to compute. Now we want to compute alpha naught n using 7. We can do that. And we're going to use something we already discussed in this course. We're going to use orthogonality. See, there were many reasons to think about orthogonality. We're going to use orthogonality. So I'm going to think this is, if you like, this exponential is a mode shape in time. You may or may not want to think of it quite that way, but I think it'll be clear why you might want to think of it that way. What I'm going to do is I'm going to multiply equation 7 by a term that looks almost like this, except I'm going to use a particular integer value. I could use 1, 17, 36, but I'll call it m, some arbitrary integer, which is distinct from all of these n's. And because I know the answer and I know how I'm going to get the answer, I'm going to put a minus sign in. I could put a plus sign in, but then I won't get what I want. So you can think of it, we tried it with a plus sign, it didn't work, so we thought, well, maybe a minus sign would help. So now we're going to use the minus sign. So we're going to multiply 7 by e to the minus I m omega, oh, yeah, I don't need a naught on that, omega naught t, and integrate from minus t naught over 2 to plus t naught over 2. Okay? That's the idea. Fourier did this a long time ago, became famous for doing this. Okay. Now, it turns out if you do that, you get, what do you get? Well, let's just write it down. You get alpha naught e to the minus I m omega naught t dt integrated from minus t naught over 2 to plus t naught over 2. That's the left-hand side. And on the right-hand side, we have the summation over n, alpha n, oops, wrong place for the n, alpha 0 n e to the I n minus m, right? I can combine those that way, dt, and then of course it's also integrated from minus t naught over 2 to plus t naught over 2. By the way, if I integrate over any time that includes a whole period of t naught, I get the same answer. I could integrate from 0 to t naught. I could integrate from minus 3/8 t naught to plus 5/8. I mean, but it's convenient to do this. Right? Okay, so what's the right-hand side? Well, the right-hand side is obviously equal to, it's equal to, well, I can take this. Well, how much detail am I getting? It turns out there's only one term that survives this operation, namely the case where n equals m. For any case where n does not equal to m, this integral over time is 0. It's orthogonal. These exponentials are orthogonal. Okay. So out of all of this, the only thing that survives is alpha naught m. And then when n equals m, of course, this doesn't depend on time. I just have integral dt minus t naught. So this is just t naught, right? So now I have an explicit expression for that in terms of this integral, and of course, involving the period. Right? So you give me a function of time that's periodic. I multiply it by this thing and integrate, and I produce the coefficients of the Fourier series.
Professor, should that be the sum of this term?
Sum over here on the right-hand side.
Your conclusion.
My conclusion is almost went up the board. My conclusion is out of all this sum, all these terms will prove to be 0 unless n equals m. So out of this infinite series, only one term survives. Because the integral, let me write it on the next page. The integral from minus t naught over 2 the plus T naught over 2 of e to the I n minus m omega naught t dt is 0 unless n equals m. It's an orthogonality-like condition. Okay, that's all. So I managed to extract one term out of the series, but this can be any term, right? And so once I have it, I have essentially have the answer for all terms. So alpha m naught, the other way around, sorry. Alpha naught m is equal to this integral from minus t naught over 2 to plus t naught over 2 of whatever function time you give me, as long as it's periodic, e to the minus I m omega naught t dt, and then it has to be divided by the period. Right? So that I just extracted the Fourier series, extracted the coefficients of the Fourier series. Okay, so let me call this what? So I guess that's equation 9. Okay, so let me sum up where we are at the moment. We have equation 9. We also have equation 8. Let me remind you what that looks like. Equation 8 was what we sought. Alpha as a function of time is this summation over all n of alpha naught n, which we now know, right, from the above equation. The transfer function, which is what we got from looking at simple harmonic motion. And then, of course, our factor AIN omega naught t. And what else? 7 will be important to have. 7 is alpha naught of t, of course, is written as summation over n alpha naught n e I n omega naught t. Okay. So these are the 3 key results for periodic motion. Now, let me tell you what I'm going to do, and then I'll do it, well, maybe not next time, because we're going to have this wonderful wind tunnel test. But I'll tell you what we're going to do, and then read chapter 3, if you haven't done so already. What we're going to do is now we're going to look at what is sometimes called aperiodic motion. That just means it's not periodic, right? Aperiodic motion, or arbitrary motion. That is motion that does not repeat itself, right? Well, that's easy, he said. All we need to do is take the limit as the period is pretty large, like infinite. So we're going to take the limit, and when we do that, these series, these summations, will become integrals. That's another reason to read Hildebrand and think about integral equations. All these summations are going to become integrals, and the Fourier series will become a Fourier transform. And if you're dealing with dynamics of linear systems, Fourier transforms is the way to go. And for those of you who were taught once upon a time the Laplace transforms are the way to go, not to worry. Laplace transforms are a special case of Fourier transforms. So Fourier transforms are the general case. But they're very much related. So once we do that, we will have, that's all linear dynamics for simple harmonic motion, which then led to periodic motion, which then led to non-periodic or arbitrary motion. Now there's another subset of this called random motion, and there's a special theory associated with that, and we'll talk about that. You'll be happy to learn that the transfer functions are a key part of dealing with random motion. And so that will lead us to a concept called correlation function, and its Fourier transform, which is a power spectrum. Bad name, but that's what everyone calls it. And we'll use that to compute things like the mean square fluctuations of a random motion. Basically what we're going to be able to do is we'll find out that if you have the power spectrum of alpha naught and you multiply by the square of the transfunction, you get the power spectrum of the output, and the integral of the power spectrum overall frequencies will be the mean square. And we use that in a variety of contexts, including gust response, because gusts tend to be random-like objects. When they do gust response in Israel, do you use power spectral density? You use, okay, fine, good. So people really use it then. I mean, in the not too distant past, people sort of avoided the power spectral density formulation because you can do gust analysis another way. But probably the most rational way to do gust analysis is using the idea of random inputs and random outputs, and that's what many good organizations do, the ones in Israel. Okay, let's stop here for the moment. But before we conclude, any questions about what we've done today?